Yes, am I audible? Is my voice is audible to you?
Yes, sir.
Yes. Can I start the session?
Yes, sir.
Okay, right. Thank you. Now, continuation to the photo edition. Yesterday we have discussed about the photo edition between the benzophenone and isopropyl alcohol. Similarly, benzophenone can also undergoing the photo edition reaction, that is photo reduction reaction, in presence of toluene. Here the toluene carbon, you know that this is the toluene. This is the toluene. It's known as benzoylic position. This is the position is known as benzoylic position. Here, these protons are active protons. These protons are active protons in presence of ionic conditions or in presence of free radical conditions. This CH bond can easily cleave, then produce the radical in case of photochemical condition. In the case of ionic reaction conditions, they produces the carbocation and carbocation, that is a benzyl carbocation and a benzyl carbanion. At the same time, H plus ion, H minus ions are released. But here we are going to discuss about the photochemical conditions. Then it releases the, when the CH bond is broke down homolytically, then leads to formation of C radical of benzylic in, at the same time a hydrogen radical will be generated. Now this is undergoing the reduction with photo reduction with benzophenone. This is the benzophenone. Whenever this benzophenone is irradiated in presence of toluene, that is the toluene mediated reaction. In photochemical condition, it leads to the formation of same benzophenol. This is called as benzophenol. At the same time, the benzyl substituted 1,2-diphenyl methanol is generated. Or we can also call it as, look at here. First, you take that structure pH, then this is a CH2 pH. Now, if you're going to give the numbering, here it starts the numbering 1 and 2. Now, 1, 1, 2 triphenyl is known as triphenyl ethanol. Its name is 1, 1, 2 triphenyl ethanol. And other product, dimerization takes place. Dimerization takes place by these toluene molecules after formation of toluene radical or benzoyl radical, which combined with another toluene radical or benzoyl radical, that is the formation of 1,2-diphenyl ethane. 1,2-diphenyl 1, 2-diphenyl ethane. These are the products. How these products are generated? If you observe yesterday's mechanism, now you can understand that what are the possible free radicals. What are the possible free radicals are? First, the CH3 undergoes the photochemical homolytic cleavage of the CH bond that leads to the formation of CH2 radical, at the same time H radical. Now, this radical associates with the benzophenone or interacts with the benzophenone. Now, this 5 bond undergoes the homolytic cleavage that leads to the formation of the pi bond is opened, that is OH is generated. At the same time, diphenyl carbonyl carbon radical is generated. Right. Now, this radical is more stable than this OH. Suppose the two structures are possible, that is R, whenever the OH is interacted with the OH, now the secondary radical is generated. At the same time, oxygen radical is generated. When we compare these two, the second one, this is the first second one, this is the first one. The first one is more stable than the second one. First one is more stable than the second one. The reason is we see that whenever we are comparing the, even though oxygen is having electronegativity, electron density increases, its stability maybe increases. But here, the carbon is attached with oxygen to phenyl rings. Carbon is attached with oxygen and one hydrogen to phenyl rings. Here, when you're going to discuss about the electronic effects, these two are the minus mesomeric effect. These are electron withdrawing group. Therefore, whenever the electron density is low, it readily accepts the pair of electrons. Similarly, whenever it is undergoing the homolytic cleavage, this pi bond, the OH radical is O minus O radical is obtained, C radical is obtained. The OH, due to the high reactivity of this oxygen, this radical easily homolytically donated to the hydrogen radical when you compare to the carbon radical. That is the reason this type of intermediate is obtained more probable than the second type. Due to that reason, the first one, when you compare the stabilities, the first one is more stable than the second one. Right? Now, this radical pH, C radical OH attached is generated. Now, we can call it as a, if you give it a numbering one, it is a methanol actually, right? 1, 1, diphenyl, methyl radical, methyl hydroxy, 1 hydroxy, 1 hydroxy, 1, 1 diphenyl methyl radical. Now, along with this is the intermediate generated. Now, the second proton where it is obtained, again, it is reacting with another toluene, in presence of the radical. Now, again, it is undergoing the CH bond cleavage, homolytic cleavage. The hydrogen radical is transferred to this radical position. Now, here OH is there. Hydrogen, newly coming hydrogen is generated a bond here, CH bond and CH. Now it leads to the formation of again benzyl radical is generated. This benzyl radical or toluene radical is generated. Now this toluene radical and this toluene both will combine together. It leads to the formation of CH2, CH2, right. Now 1, 2 diphenyl ethane is generated. 1, 2 diphenyl derivative is generated. Okay, this is known as photoreduction. This photoreduction can also take place in presence of amines. That secondary and tertiary amines can also lead. Sometimes amides are also leads the photoreduction reactions. Okay, some examples here. Same benzoquinone. It is the standard one I am taking for remembering. Yes, benzoquinone is undergoing the photoreduction in presence of secondary amine or CH2 NHR. This is a secondary amine. This secondary amine This photochemical interact with the benzophenone. Now, in the photochemical condition, the first it is transformed to N25 star triplet state energy. It will be collide with this one. Then it leads to abstraction of proton. That abstraction leads to the NH bond will be homogenetically cleaved. Then the hydrogen is generated from this nitrogen. This hydrogen radical is interacted to this carbonyl group. 2 moles of secondary amines are participating in this reaction. That leads to the formation of imine derivative from the secondary amine, and alcohol as well as dimerization is also takes place from the uh, benzophenone. But here the most probable product is dimerization of whatever the alcohol radical is generated in this reaction, that will be participating in the dimerization reaction, that leads to the formation of benzophenol derivative is generated. Benzophenol derivative is formed. Uh, then what is the major product in this reaction? The benzophenol is the major product. Major product is benzophenol. I have already explained how benzophenol is generated. And the second one is, yeah, sometimes here the second amine molecule may not be available. In such case, the second radical is also abstracted from this carbon. Abstracted from this carbon, that leads to the formation of imine derivative. This is the imine derivative. This is the benzophenol. This is the major product. This derivative is automatically obtained from the whatever the reactant used in the secondary amine, that is the imine. Okay, this is the imine mediated, secondary amine mediated Benz photoreduction reaction. Photoreduction reaction. Next, if you take the tertiary amines can also participating in the photoreduction. If you take the aryl, here R is the aryl group, aromatic benzene like naphthyl, phenolphthalein, anthracene like derivatives. Structures rings may be attached to that position. That is reacting with tertiary amines, RCH2. Here the necessity is whether it is a secondary amine or tertiary amine, whether it is a secondary amine or tertiary amine, at alpha position should have protons. In previous case also we've seen that at the alpha position we have the hydrogens and the carbons. Those hydrogens are also participating in the photoreduction reaction, because the reduction reaction means the source required is hydrogen. Whatever the reactant participating in the reaction is acting as a reducing agent, that need to provide the hydrogen radical or hydride ions or protons to the reaction. Here also in the photochemical condition, the secondary amines are acting as a reducing agents. Therefore, it needs to provide the hydrogen radicals to the substrate. Okay, that leads to the formation of product. Now here it leads to the formation of product, that is first it is generating the aryl radical OH, at the same time RCH radical. Here there is no proton here. On the tertiary nitrogen, there is no protons or there is no hydrogens. Due to that reason, there is no involvement from the secondary amine, tertiary nitrogen. Here, this hydrogen, alpha carbon can able to donate the hydrogen radical to the O radical, which is generated in the reaction. Later, it combined together, it produces the aryl OH. This reaction is involving the homolytic bond formation between the carbon radical obtained from the tertiary amine and the carbon radical which is obtained from the aromatic ketone. Now it leads to the formation of CH N R R prime. This is the tertiary amine group, and R. This is the product. This is the major product obtained. when the tertiary amine is participating in the reaction. When major product is obtained as this substitution reaction. Right. Now, this is also known as photoreduction. Photoreduction. Yeah. Coming to the next reaction, it is also similar to the photoreduction type of reaction. That is Paterno-Bichi reaction. Several reactions are there. You can see, you can read your observation, your manual. You need to learn some examples also. So many examples are given in our book. Please follow your book. If additional examples are required, you can follow that. Okay. Before going to the Petronovich reaction, the type of intermediate, the type of mechanism is participating is already explained. But again, I am going to explain here. Suppose aromatic ketones, sorry, aromatic ketones are participated. Then, whenever it is when we are irradiated with light, it generated first singlet state. The singlet state, that is that N25 star, N25 star singlet state. Now this leads to the generation of aromatic triplet state, aromatic benzophenone, aromatic ketone triplet state. That is N25 star triplet state. Now it will collide with, if you take this previous example, tertiary amine. That leads to the formation of this triplet energy transfer to this the secondary carbon. Now here it is known as electron transfer, and it is the rate determining step, and charge transfer step. Step is known as charge transfer step. Then it leads to the formation of, whenever the electron is transferred, it leads to the formation of two radicals. One radical is aryl radical oxyanion. This is radical oxyanion, and the tertiary amine produces radical cation. That is, the radical is generated at nitrogen and R. Here the radical is there. Here this arrow indicates that not the electron transfer, triplet state energy transfer. During that process, for getting stabilization, the electron is taken from this electron donor. The triplet state energy, this is colliding with this tertiary amine. In this case, it transforms exchanges the triplet state excited state energy. Suppose it is a 64 kilocalories or 74 kilocalories, like that. Approximately 69 kilocalories. This energy is transferred to this tertiary amine. When this will be excited, immediately the electron transfer or charge transfer takes place. This electron is transferred to the oxygen. Now oxygen getting the negative charge. Again, here this is undergoing the homolytic cleavage that leads to the formation of oxygen is having a one odd number of electron along with one nitrogen electron. Therefore, it is getting negative charge. At the same time, this pi bond is undergoing the homolytic cleavage. Therefore, this carbon getting the radical. This is known as radical oxyanion or radical anion, or also called as radical anion. Coming to the second one, once this is in the activation, it reaches to activation state, highest energy, this electron is transferred to this ketone. Now it gets the positive charge. Right? Here there is no charge at that position. This is known as, here the nitrogen is having the one odd electron. Simultaneously, it carries the positive charge. Due to that reason, this is known as radical cation. Radical cation. Now, in the next step, what's happening? This excited state, to get the stability, this hydrogen undergoes the homolytic cleavage, or look at here. Here, ion charge, ion exchange, or otherwise, here it is not takes place the homolytic cleavage. This carbon hydrogen bond pair heterolytically, this carbon hydrogen bond is heterolytically cleaved. This carbon hydrogen bond, sigma bond, is donated to the nitrogen. Now, this positive charge will be neutralized. Then it leads to the formation of H plus ion. This H plus ion is taken by the whatever the radical anion generated. Now it leads to the formation of this intermediate. AR, OH radical. Now, whatever the intermediate coming from after the hydrogen proton is transferred, R, CH radical is there, and a double bond is already generated, and already the required lone pair is required to nitrogen, that is achieved from the this heterolytic transfer of electrons. Then here the radical imine radical is generated. This is known as imine radical. This imine radical, that is the odd electron containing on carbon, and odd electron containing or radical containing on the carbon. This carbon. This is known as tertiary carbon. Both will combine together homolytically. That leads to the formation of final product. This will be generating the required product. What is that here? Oh, previously yes. These two reactants combine together, that leads to the formation of OH, AR. This is the product. This is the product obtained in the reaction. This is the mechanism. Now you need to understand that here the mechanism involving the first one is it forms the triplet state energy. After the transfer this triplet energy to the tertiary amine, simultaneously it excited. Then due to the excitation or activation, that electron is taken by the oxygen present on the carbonate. Then it leads to the formation of radical anion. This radical anion, simultaneously radical cations are generated. After formation of this radical anion, radical cation, this carbon hydrogen bond will be cleaved heterolytically. The carbon hydrogen bond electron transfer to the tertiary amine. Then it generates the H plus ion. This H plus ion is taken by this anion, oxyanion. Now it leads to the formation of this kind of radical. Simultaneously, it leads to the formation of imine radical. This imine radical and this radical both will combine together. It leads to formation of this product. Right. This is about the mechanism of photoreduction involving tertiary amine of carbonyl compounds. Okay. Next, coming to the Petronovich reaction. All the reaction here discussing are important, especially in the first unit, the second unit. We are going to discuss about the photoreduction and Petronovich, Norris type cleavages. In this, especially this chapter, where some named reactions are there. These named reactions are very important. Every time we are encounter these named reaction, that is the first one, we can write them. Photoreduction, photoreduction. The second one is the Petronovich reaction. Petronovich reactions. Third one is Norris type cleavages. Norris type. And isomerization of benzene and photoadditions of olefins. And the sixth one is Barton reaction. These are the most important commonly observed questions. These are six. And sometimes some other questions are also observed, but that is depends on the paper method. Okay, but you need to remember these six. Yeah, very much important. Six are very much important for the exam purpose. Right now, coming to the second one, Petronovich reaction. Petronovich reaction. In this reaction, here also this is the part of carbonyl photochemistry of carbonyl compounds. Now here the carbonyl compounds on radiation in presence of olefins, they forms oxyacyl oxacyllobutane derivatives. These are called as oxytanes. Oxytanes. Again, I am repeating. Whenever you are taking the carbonyl compounds, these are the carbonyl compounds. In general, I am taking this R prime. Both are. This will be combined with the olefins, like this kind of olefins. Here I am taking R double prime, R triple prime for differentiation of substitutions. Now, this together, if we are irradiating, this mixture is irradiating, that leads to the formation of that oxytane, a four-membered oxygen heterocyclic derivative is generated, that is R prime, R double prime, R triple. This is the substitution. Okay, these are the common products when carbonyl compounds are irradiated along with olefins. Now, what are these products? This product name is oxytane, or elaborately oxacyl right? Oxacylobutane, oxacylobutane. Oxacyclo. Cyclobutane. Okay. Now, based on the products formed, How we can define the Petronovich reaction? Carbonyl compounds. Carbonyl compounds on irradiation along with olefins produces an oxacyclobutane or oxetane oxygen heterocyclic, oxygen 4-membered oxygen heterocyclic, 4-membered oxygen heterocyclic is generated. This reaction is called Petronovich reaction. This is the reaction is known as Petronovich reaction. First, come to the mechanism. Benzophenone, or I'm taking the benzophenone as example because here the triplet state energy is required. Due to that reason, I'm taking a benzophenone. This benzophenone on irradiation. First, it is in the ground state, S0. Now, it is on irradiated. It leads to the formation of singlet state. This singlet state undergoes the wavy arrow intersystem crossing. That leads to the formation of a benzophenone triplet state energy. Benzophenone triplet state energy is entered by star transition. Now this will undergoes the reaction with olefin. Here I am going to take olefin is 2 hydrogens. Here the 2 methyl groups are there. 2-methyl propene is the other reactant. Now first then explicit means like this. The activated benzophenone, a transition complex is generated. A transition complex, here the 2 hydrogens are there. It will less steric entries between the hydrogens than the methyl. Due to that reason, a transition, just an interaction will be generated. This is known as, this situation is known as Xplex. Just almost it is a transition state, not a, it is the hypothetical one. There is no particular evidence for this. Now, this leads to the 2 kinds of biradical intermediates. It leads to the formation of 2 kinds of biradical intermediates. What are that? Look at here. PH, O, CH3, CH3. Here the radical and the 2 benzyl radicals. Right. And another one. Look at here. It's the formation of the benzyl radical is common in both the cases because already explained this radical is more stable than the radical present on oxygen. Okay. CH2 radical. This is the CH2 radical. This CH2 radical. This will be generate the CH radical. Now, again the methyl groups are like. Look at here. When we are Just I'm showing this approach is near to each other for the next step, but this may not be arranged like this. Okay, they may be arranged like this, even though they forms the same intermediate oxygen here. Now, like this, CH2, CH3, CH. In the photochemical condition, they may undergo the several conformation. That's the conformation they may be arranged in different kinds of manner. But whenever during the reaction they undergoing the flexible manner, the flexible manner is arranged due to the CC bond rotation, CO bond rotation, and C like that. Okay, the rotations are happening. When the next step is proceeded, the both the radical biradical systems are associated together. They produce the next step. But here I am comparing the which one is more stable. Two biradical intermediates are generated. Two biradical intermediates are generated. In the two radical systems, almost the arrangement is same. Arrangement is same, but here it involves this radical and this radical involves both are. This is the tertiary radical. This is the diphenyl benzyl radical. That means this is the benzyl radical type. Benzyl radical. That means the radical is attached with the two phenyl groups plus minus mesomeric effect. Therefore, this electron, odd electron, is more stable on this carbon. Similarly, this carbon radical is also more stable. When we come into the comparison, we can here the radical which is present on carbon, trityl carbon ion, sorry, trityl carbon radical is more stable when the carbon is attached with two phenyl rings. This is the not RH, pH. Okay, then pH, hydrogen, which is simple benzyl radical. This is the order of stability. This is the carbon which is also attached with the three phenyl. This is the radical which is more stable, and then this two phenyl rings attached, and then the one phenyl ring. Now this is also more stable than the tertiary one. Simple carbon is attached with the alkyl group. Simple three alkyl group, that is the tertiary alkyl radical. Now this tertiary alkyl radical is more stable than the secondary. Secondary is more than the primary. This is the order of stability. Order of stability. Then you can hear in the both the radicals are almost, this is the highest radical and the second highest radical. This is the second highest radical stable in the chart. This is the from bottom to third. Now this is also more stable. When here the second highest radical stable one, and this one is the least stable one. When we comparing both, this will be cancelled whenever we are recognizing stabilities. But compare these two. This is the primary radical, and this is the tertiary radical. In the tertiary and primary radical, which one is more stable? Automatically, tertiary radical is more stable. Therefore, the tertiary radical containing biradical system is more stable than the primary radical. Therefore, it is more stable biradical, more stable biradical. Intermediate. This is the less stable biradical intermediate. Now, for other steps, it is undergoing the cyclization. Cyclization that leads to the formation of an oxidane derivative. pH, pH, and CH3, CH. Now, this will lead to the formation of, this is also undergo cyclization. but less amount is generated, maybe the less amount of product is also generated. Then this is the major product, because the stability of the biradical intermediate is more. Due to that reason, it generates the major product. And the second one is, it is a less stable biradical intermediate. That is the reason it is the minor product. This product is known as minor product, right? This is the mechanism involved in that. But the reaction condition, it depends on the reaction condition. Whenever we are going to explain this in the numerical value strengths in the stabilities, look at here, the reaction between the N2 pi star triggered state of benzophenone and ground state of isobutylene leads to the formation of exciplex excited complex. This is the exciplex complex. This is the exciplex complex. Okay, which collapse to form the more stable intermediate. Here the two possibilities are there. The two possibilities, one is the more stable. Therefore, this will be generated. The more stable means the CO bond in preference, CC bond and CO bond, CO bond and CC bond energies are 88 kilocalories and kilocalories per mole, and CC bond is 80. Sorry, CO bond is 88 kilocalories and CC bond is 80 kilocalories. Therefore, based on that, the CO bond is generated first. Due to that reason, then the next step it can easily undergoing, because it is the rate determining step for the formation of biradical intermediate. Next, it is undergoing the CC bond formation, that it's a lower energy. It is associated with lower energy, therefore it easily combined together, that leads to the formation of cyclic system. Okay, the resulting diradical or biradical cyclizes to yields to 2,2-diphenyl 3,3-dimethyl oxetine. This is the 2,2-diphenyl. The numbering starts from here. Its IUPAC name is the numbering. Now it is 2,2-diphenyl, 3,3 dimethyl oxetine. This is the product. Whenever we are comparing the ratios, here almost the ratio is major product and minor product. Almost 98% is this product, and just 2% is this product. 98 and 2%. That is the comparison, right? The same reaction is carried out. The ratios will be changed. That is, the reason is formation of different biradical intermediate. Like look at here. This is the benzophenone. The same benzophenone is taken for comparing the yields of the products. Now, 2-methyl-2-butene is the reactant. 2-methyl-2-butene is the reactant. Now, which is on irradiation, that leads to the formation of two products. I don't want to again explain the mechanism. The same mechanism they are following. Both the reactant they follows the same mechanism. CH3. This is the one, and CH3, 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 the pH. Now this is 90% of yield it obtained, and 10% of yield is obtained here. 90% is here, 10% is here, right? Then what kind of intermediate is generated in between them for the bionarration? Look at here. Just to cleave it, biradical intermediate will be generated. The CC bond formation, pH before the CC bond formation, you cleave with the CC bond. This is one biradical or biradical system, and second intermediate, it is also biradical intermediate. CH3, CH3, PH3, PH. No, this is also direct. Now coming to that, there is no comparison here. Both are same radical. Then this, in the stability factor, these two are not affected. When comparing these two radicals are compared. This radical is tertiary radical. This radical is secondary radical. When we comparing the stabilities, tertiary is more than the secondary. Due to that reason, the more stable intermediate is this one. This is the more stable, and it is less stable, but it is stable somewhat the primary radical. Due to that reason, in the reaction in between, if you stop the reaction at the middle state, the ratios are also obtained. The 90% approximately, more or less 90% of intermediate is obtained this radical, and approximately more or less 10 10% of this radical will be recovered. Okay, based on that, the products are also generated. 90 plus 10 ratio of the mixture is generated. This is the major product because it is up to 90% is the minor product. This is the less, only 10% is generated. Okay. Now coming to stereochemistry of Petrovich reaction. Okay. Sometimes here the olefins are also, not only olefins, it can also observe the Petrovich reaction in the alkynes. When you come into the alkynes, also undergoes the addition reactions with the carbonyl compound that leads to the formation of cyclic oxytenes. Oxytenes will be generated. This is also known as Petrovich reaction. Okay, here what's happening? Alpha beta unsaturated carbonyl compounds are generated after formation of cyclic compound that will be cleaved to generate the alpha beta unsaturated carbonyl compound. That means here the carbonyl compounds is mixing with alkynes, and on irradiation it leads to the formation of oxytene derivative. This oxytene derivative further rearranged to alpha beta unsaturated carbonyl compounds. What's happening? How it is happening? You see this. Okay. Phenyl, along with, I'm taking tertiary butyl, taking N-butyl attachment, N-butyl, that is 5 comma 5 dodecyl, decyne. Is 5 decyne. Right. Now, which is undergoes the Petrovich reaction that leads to the formation of an oxytane derivative. The product is like this. Here the symmetrical alkyne, that one, that is the reason the product is also butyl group here. This product is generated. After formation of this product, a rearrangement is taking place. How it is undergoing the rearrangement reaction? Look at here. This oxygen, this carbon oxygen is broken. This bond is migrating to here. These 5 electrons are first initiated. These 5 electrons are initiating to migrate this position. Then it leads to the transfer of this bond electrons to this position. Why? These 5 electrons are this 5 bond is the isolated double bond. When the isolated double bond is there, suppose H2 CH double bond CH. This type of arrangement is there. So this type of arrangement is there. For example, this one. Just suppose it carries the positive charge, it carries the negative charge. This negative charge is donated to this carbon. Now these electrons are donated to this position. Now alpha beta unsaturated is generated. Look at here. This bond here also it is like this. The result product, you see that this is the product. Okay, look at here. One, this is the alpha, this is the carbonyl group, this is the alpha, this is the beta. Here the advantage is increasing the isolated double bond length. Then that's why the ring system is having some strain. That strain is released, it is on opening, the first thing. And the second thing is also playing the important role is alpha beta unsaturated or isolated double bond or conjugated chain length is increasing. When the conjugation is increasing, the stability is also increasing. Now, this ring cyclic system is undergoing the ring opening reaction that leads to the formation of this product. This is known as alpha beta unsaturated carbonyl compound. Okay, the mechanism is same. Whatever the mechanism explained to the olefin, the same mechanism is applicable for this alkynes also. Right? Now coming to stereochemistry of petroleum reaction. When aliphatic carbonyl compounds like acetaldehyde, acetone are reacting, involving in the Petrovich reaction, they proceeds through the reaction that is the formation of N2 5 star singlet state. Then which react with the cis or trans olefins to give produces a singlet biradical system. This singlet biradical immediately cycles to give the stereospecific product. The stereospecific means only one product is generated. Only one product is generated. So suppose you take a benzaldehyde as per previous conversation. This is acetaldehyde, a simple aliphatic aldehyde. This aliphatic aldehyde is undergoing the Petronovich reaction with the trans or cis olefins. This is the 2-butene, cis-2-butene. This is cis-2-butene. Similarly, the same reaction is carried out with trans-2-butene.
Right.
Trans-2-butene. Now, what's happening here? Only one kind of intermediate is generated because this is a symmetrical olefin. Suppose this kind of olefin is there, that is the unsymmetrical. Right. This is also unsymmetrical. Now, this kind of olefins can generate the two biradical system, but it is the asymmetrical. This carbon is having one methyl group substitution, this carbon is having one methyl group. In the cis also, trans also, same structure is same, but the structural arrangement is different. That is the geometrical isomerism. Geometrically, the structures are different only, but the structure is same. Now, the olefin system is symmetrical. This symmetrical olefin interact with the acetaldehyde that leads to the formation of only one intermediate. Only one intermediate. But this intermediate orientation is different. This intermediate is generated. Suppose here the intermediate is generated like CO, take CH3. Generally, this intermediate is generated CH and CH2, CH3, CH. Okay, this kind of intermediate is generated. Here, the methyl groups may be both are cis, both are oriented to above the plane, or both are oriented to the below the plane. Now, these two intermediates are like this. I'm showing here CO, that is the OH CH3 group is arranged above the plane, and the hydrogen is arranged below the plane. Now, the first kind, both the methyl group, both are cis, therefore arranged above the plane, and the hydrogens are below the plane. This is one kind of diradical, and the second kind of diradical. What is that? Both the methyl oriented to are arranged to below the plane. The hydrogen are above. Hydrogens are above. Now this leads to the hydrogen. This kind of orientations are shown by the intermediate. This is singlet. This is also singlet biradical. Singlet diradical intermediate, and this is also singlet diradical intermediate. Now it leads to the cyclization. Leads to the cyclization that leads to the formation of cis methyl is there. Hydrogen is below the plane. Hydrogen is below the plane. CH3. And CH3 is above. And hydrogen is below. Now all the methyl groups are above the plane. Therefore, this is cis. Both are above the plane. Here also this is also cis. Now the product is cis comma cis. This is numbering. I'm giving number 1, 2, 3, 4. 2, 3, 4. Trimethyl oxetine. This is the product. Similar. The second kind of intermediate. These two are also undergoing the cyclization. This biradical system is also homoletically associated, that leads to the formation of sigma bond. Now, the methyl group is above the plane, the hydrogen is below. Here, the two methyl groups are below the plane. For that reason, after the reaction, also the methyl groups are also oriented to the below the plane. Now, this methyl group is above the plane, this methyl group is below the plane. Now, this is trans. These two methyl groups are same and the below the plane. Therefore, cis. Now, the product is cis trans 2, 3, 4 trimethyl 2, 3, 4 trimethyl oxetine. This is the product. This is the product. Right. Now, if you come into the trans, these are the two products are generated by the cis isomer. Cis isomer, that is the cis-2-butene is undergoing the Petrano-Bucci reaction with the acetaldehyde that leads to the formation of two intermediate, but the two intermediates are 50-50%. Okay, 50-50%, right? Similarly, the trans product is also generating. Again, I'm not going to explain the mechanism. You can understand the orientation. I will show them for the understanding. Avoid the difficulty to understand. Again, yes, two intermediates are generated. Here, for our remembrance, you need to arrange the acetaldehyde methyl group is above the plane. Now the remaining this olefin is the trans olefin. One methyl group is above the plane and one methyl group is below the plane. Then remaining hydrogens are arranged like this. Now this is the one kind of diradical, and the second diradical CH3 hydrogen. Here the methyl group is below the plane and the CH3 group is above the plane, and arrange the hydrogens. This is another kind of radical, right? Now this leads to the formation of one product. The product is CH3 group is below, hydrogen is above, and hydrogen is below, CH3 is above, right? Methyl group CH3 is above, hydrogen is below. Now both are in the same side. When you come to 1, 2, 3, 4. Now both are on same side, trans. Both are of same side, trans. Both are of same side. This is cis. This is cis. Both are of them opposite side. Therefore, this is trans. Now cis, trans, 2, 3, 4, trimethyl, cyclooxytene. You can simply call it as oxytene. Now the second product. So hydrogen is below the plane, this is above the plane, and this is the CH6 below the plane, hydrogen is above the plane. Right. Here both are opposite to each other. Trans. Both are opposite to each other. Here also trans. Now the product is trans, trans, 1, 2, 3, 4, trimethyl oxytane. Trimethyl oxytane. This is one product. Look at here, the products obtained by the cis isomer is different from the products obtained by the trans. But here the product ratios are also 50-50%. Here also 50-50%. Therefore, whenever the same reaction is conducting benzaldehyde, suppose the benzaldehyde instead of acetaldehyde is conducting with the reaction with the mixture of cis and trans 2-butene, the products are 4 products are generated. What are the 4 products? The mixture. 4 products are generated. The products are one product, that is cis, all cis product, cis isomer. Next. PH. Now this is the trans, this is the cis. Trans cis product. Next, CH, CH3, hydrogen, CH3, hydrogen. Then the cis trans product, But here the groups are different. Here phenyl group is methyl group is here methyl and methyl comparison. Phenyl and methyl groups are compared, and here methyl and methyl groups are compared. Now the last one is trans product. The methyl group, hydrogen, CH3 group, hydrogen, phenyl, and hydrogen. This is the trans product. How these products are generated, you need to work out at your home, and how different kinds of diradical systems are generated. In that, you can write, imagine that how these are generated. Okay, for the formation of these four kinds of intermediates, I'm giving the how diradical systems are arranged. Suppose the benzaldehyde is on irradiation. In the previous case, the intermediate is both all the intermediates. First, it is excited. This excited one is only generated singlet excited state. This singlet excited state collide with this intermediates. Here also same. These are trans intermediates. That is the formation of four products. Similarly, here also four products are generated in the case of benzaldehyde. But the reason is it undergoes the three phenomena. So one is bond rotation, spin inversion, cyclization. First, you need to understand the step by step. Whenever you are irradiating the benzaldehyde with the sunlight or UV light, then the first generates the singlet excited state into 5 star, which is undergoing intersystem crossing that leads to the formation of benzaldehyde triplet state N2 5 star transition. Now this will be colliding with the cis or trans to butane. Now it leads to the formation of two kinds of intermediates. What are the two kinds of intermediates? Look at here. I'm trying to. Yes. Two kinds of intermediates are generated. One is PH3, PH3, H, PH3, H. Same arrangement, PHs, but there is no change. Here the cis one. Okay. Again the cis one. And another two from the trans. These two are from the cis. And the next two. Here the CH3 is in the trans manner. This is one diradical. This is another diradical. This is another diradical. Yes. CH3, H. Yes, four diradicals are generated. These four diradicals combined together, whatever the radical array generate, this produces four products. The four products are given here. What is that? Here instead of okay, 1, 2, or you can take it A, B, C, A, B, C, D. These products are generated here. Products are generated here. How? Here the reason is I am showing 4 at a time. You can take cis isomer only in this Bertanovich reaction. These 4 products are observed. Or you can if you take the trans isomer only, trans 2-butane is treated with the benzaldehyde. Then even though these 4 products are generated, the reason is whatever it may be intermediate is generated in the reaction, they undergoing the bond rotation phenomena. Bond rotation is bond and spin inversions. Here the biradicals may be arranged in the triplet energy state, both are having the same spin, or parallel spins, single state. Okay, during the cyclization, they may undergoing the spin inversion for reaching the required energy. Therefore, spin inversion, it participating in the spin inversion, right? Next, later it is undergoing the cyclization. These 3 steps are involved. These 3 steps can lead to the formation of 4 products, even though we are taking the cis isomer only in the reaction, or we are taking the trans isomer only in the reaction, that leads to the formation of 4 products. Okay, this is the stereochemistry of Bertanovich reaction. Now, coming to side reactions of Bertanovich reaction. Side reactions, generally, this along with the side when the olefin possesses allylic or benzylic hydrogens, photoreduction takes place along with the Bertanovich reaction. Photoreduction may also appear in the reactions. Suppose if you are looking for Bertanovich between the benzaldehyde carbonyl compounds and olefin, at that case, if the olefin is having any phenyl ring and phenyl benzylic position phenyl rings or allylic system with alpha hydrogens, that leads to the directing the reaction towards the photoreduction instead of Bertanovich reaction. In such cases, the products are obtained Bertanovich products along with the photoreduction products. For example, here side reactions. Side reactions of Bertanovich. Reaction. Right. This is benzophenone. This is 2-methyl-2-butene. 2-methyl-2-butene. Now here, if you see that these positions are allylic position. What is allylic? CH3, CH double bond, CH2 is there. Now it is undergoing a resonance. It leads to formation of R. So the double-headed arrow. Okay. Resonance structures will be generated. CH2 double bond, CH. These resonance structures will be generated. During the formation of this resonance structure, the proton is exchanged between this 1 and 3 carbon. Similarly, here also there is a 9 hydrogens are there. Therefore, 9 into 3, at least 27 resonance structures will be generated. Okay, due to the presence of this allylic position, this reaction gives the oxetane as the Bertanovich product. Oxetane as a Bertanovich product. Simultaneously, photoreduction products are also generated. Okay, now this mixture is irradiated with light. After several excitations, it reaches to the benzophenone, reaches to the tribulate energy state that will be collide with the that 2-butene, 2-methyl-2-butene, that leads to the formation of 64% of oxetane. Oxetane product percentage is 64%. This is Petronobuchi product. Next, a dimer is generated. A dimer is generated, that is CH2 double bond CH, CH3, CH3, and this is the dimer. This dimer is generated. We have seen that dimerization is also takes place in the photoreduction of the benzophenol. Right, benzophenol is generated due to the dimerization. Right, CH2 double bond CH3, CH3. This is also dimer product, and along with other products, C10, a fully saturated alkane is generated. Now, these three products, the first one is Petronovici product, but the second, third, and fourth. Second, third, and fourth. These are the photoreduction products. Photoreduction products. Now, in the case of Petronovici reaction, the side reaction may lead to the formation of photoreduction products when the reactant olefin is having a benzylic or allylic positions are there, or benzylic allylic substitutions are there in the olefin, that leads to the, or that competes to the Petronovici reaction. Photoreduction is competes the Petronovici reaction when allylic and benzylic positions are present. Okay, so many examples are there. You can read it and understand it in from your book. Okay. Now, coming to the Norris type cleavages, the second, third important named reactions, Norris cleavages. Just I will give you the definitions of Norris type cleavages later. In the next week, I will discuss it in detailed manner. Today we have only 7 minutes of time. Due to that reason, I will just briefing the definition of the Norris type cleavages. Okay, Norris cleavage. Here, these Norris cleavages are classified into two types of Norris cleavages. One is Norris type 1 cleavage. Norris type 1 cleavage. These are known as alpha cleavages. Also called it as, these are known as cleavages, alpha cleavages. These are known as alpha cleavages. The first type is, and the second type is Norris type 2. Norris type 2 cleavage, that is beta cleavage, or beta bond will be cleaved due to the reason that is known as beta cleavages, or gamma hydrogen transfer or abstraction. Okay, Norris type 2 cleavage, this is known as beta cleavage or gamma hydrogen abstraction. Gamma hydrogen abstraction. Okay, these two types cleavages, how very much important for the carbonyl compounds reactivity. To understand the photochemistry of carbonyl compounds, you need to understand, if you need to understand the photochemistry of carbonyl compounds, these two reactions are very much important after the photoreduction and Petronovici reaction. Now coming to the first one, Norris type 1. In this Norris type 1, suppose you take the carbonyl compound, because these are the characteristic reactions of carbonyl compounds. Characteristic reactions of carbonyl compounds. For that reason, you need to take the starting materials are carbonyl compounds. Suppose R prime. When only the single molecule, you no need to add the other reactant, single molecule is irradiated with the light, then you know that this is the carbonyl group, this is the carbonyl group, right? At the adjacent bond, directly linking adjacent, this is the carbonyl compound. Other than C double bond O, the next attachments or next sigma bonds are known as alpha bonds. They are known as alpha bonds. Now these alpha bonds are undergoing homolytic cleavage whenever we are irradiating with the light. These are undergoing homolytic cleavage. The first one, it is undergoing first homolytic cleavage of alpha bond that leads to the formation of this radical. Right? And simultaneously R prime radical. Whatever the alkyl group is there, that is generate the two radicals. Two separated radicals will be generated. This is known as alpha cleavage. Alpha bond will be cleaved. Due to that reason, alpha cleavage is known as alpha cleavage. In this alpha cleavage, why it is happening? Why it is happening? When you coming to the structure of orbital structure of carbonyl group, this is the C double bond O. How C double bond will be generated? I will show you. This is sigma bond, and no need to explain the sp3 hybrid orbital and sp hybrid orbital both will be combined together. They produce the sigma bond, and this is having one unhybridized p orbital, one unhybridized p orbital, and this is having another unhybridized p orbital. Right? Oh, sorry. Yeah, sp2 hybrid orbital. It is an unhybridized p orbital. This is unhybridized p orbital. Both will be combined together. They produce the pi bond. Yes. Next, the sigma bond between them. This carbon is having sp2 hybrid orbital. Is binding with the sp3 hybrid orbital of an alkyl group. sp3 hybrid orbital of an alkyl group. Now, these two are look at here. This is the oxygen. This oxygen is highly electronegative. This oxygen is highly electronegative. Therefore, these 5 bonds are more towards oxygen. More towards oxygen. Due to that reason, this bond will be very weakened. This is the sigma bond. This is the pi bond. Right? Whenever we are irradiating it with, this bond will be cleaved, easily cleaved, because it is the electron deficient. Now this bond pair is more towards. At the same time, it is undergoing homolytic cleavage. Whenever this orbital is having one, this is having a bond pair. This bond pair is equally shared by the sigma bond. Now, when it is undergoing the homolytic cleavage, this carbon takes its electron from the bond, and this carbon is taken from its bond, sigma. Okay, the sigma electron is remained here. That is R C dot double bond O. At the same time, R prime bond will be generated. Now, if you see that it can be highly stabilized. Yeah. These are the intermediates are generated. Now, these intermediate further reacting for the dimerization that leads to formation of diketones, simple alkanes will be generated, or they can recombine together. They produce the same product, right? Or it may undergo second Norris type 2 cleavage, so Norris type 1 cleavage, Norris 1 cleavage, that leads to the formation of R radical along with carbonyl is generated. Now, these both radicals may combine or R prime produce OH. These are the products. These are the products. Okay. Today I'm concluding the class. Next class, Vidya madam is waiting. Now you can join into the class. Thank you.